So this diagram shows what's going on. So we are attaching the J handle, and when we do this, there's a new boundary component created, the product of dj and Sn minus j, and this is what we're going to attach the I handle to. So here we have another diagram showing the I handle with the core, the belt sphere, and the attaching sphere. So you can show that providing that the attaching sphere of the I handle doesn't meet the belt sphere of the J handle, you can radially push off the I handle off the J handle. So you've shown in terms of the attaching sphere and the core sphere being smoothly moved off. So there is a slight caveat. You have to be careful that not only does the attaching sphere of the I handle miss the belt sphere of the J handle, but also it could be that when you thicken the attaching sphere of the I handle, it still meets the belt sphere of the J handle in this picture, in which case what you can do is you can solve this by slightly shrinking the I handle so that the thickened attaching sphere is disjoint from the J belt sphere and then pushing radially. So remember that I was less than or equal to J, so we can show generically we should be in the first situation because this attaching sphere of the I handle and the belt sphere of the J handle lie in the boundary of some n+1 dimensional ascending cobordism. This boundary is n-dimensional, and so generically we expect the intersection of an I-1 sphere and an n-j sphere to be of dimension I-j-1 when these guys live inside an n-dimensional manifold. But we assume that I was less than or equal to J, so generically they don't intersect and we're okay. Perhaps in the special case where they do intersect, you could perturb the Morse function to try and remove this problem. Okay, so now we come to another technique, handle creation. So remember with the ascending cobordism, we're attaching these handles. We can now assume that they're attached in order of increasing dimension. So we could be in a situation where we've attached some k handle, then at some later time we attach a k+1 handle, and it could be that these cancel. So here we have an example. We've attached a 0 handle, so attaching a 0 handle is just taking the disjoint union with an n+1 disk, because formally you need an embedding of s-1 cross dn+1, but that's just the empty set. And so then we attach a 1 handle, and so you can see that you can smoothly deform this new space back to the original product. So essentially we've done nothing, and here we have an example where a 1 handle cancels with a 2 handle. So we've attached the 1 handle, and for the 2 handle, well, I've only shown the attaching sphere and the core, but you can imagine once you have attached it, you can smoothly push it down. So again, you just return to the base. So again, this can be done on the level of Morse functions. So here we have a critical point of index k and a critical point of index k+1. So we can essentially remove these by perturbing the Morse function. So the question is, can we give some necessary and sufficient condition under which 2 handles can cancel? And the answer is yes. So for this, we need to return to the handle chain complex. So recall that the handle chain complex is defined as follows. So you have your handle decomposition of your cobordism. The kth chain group is defined to be the free abelian group generated by the k handles, and the differential from the group of k chains, the group of k-1 chains, is defined as follows. So there shouldn't be this factor here should not be there. So it's defined in terms of the incidence numbers, specifically the intersection number of the attaching sphere for the k handle and the belt sphere for the k-1 handle. So we have a picture here. So the boundary of this k handle is given by -1 times the boundary of the k-1 handle, because we have these intersection numbers +1, -1, -1, which give -1 overall. So certainly a necessary condition for handle cancellation is that the boundary of the k handle should be plus or minus the k minus 1 handle, which is the same as saying the attaching sphere of the k handle has algebraic intersection number plus or minus 1 with a belt sphere of the k minus 1 handle. Okay, so this is only necessary for it to be sufficient. We actually need the geometric, so set theoretic intersection number to be 1. So these guys should intersect in exactly 1 point. And then the orientation determines whether the algebraic intersection number is plus or minus 1. So this is a sort of simplification of the previous diagram where the algebraic intersection number is 1, but geometrically it intersects in 3 points. Now geometrically it intersects in 1 point, and the algebraic intersection number is 1 up to sign. So the idea was we could try to do this using the Whitney trick. So this is the situation we have. We're looking at the intersection of the attaching sphere of the k handle and the belt sphere of the k minus 1 handle. So remember, the idea was find a path from P to Q in the attaching sphere of the k handle, and then follow it round by a path from Q to P in the belt sphere of the k minus 1 handle. And this gives us a loop in, well, perhaps not in W, but maybe in one of the ascending h-cobordisms. And the idea was try to find an embedded disk in the complement of the attaching sphere and the belt sphere, such that the boundary of this embedded disk is the loop we've just described, and then the idea is to try and pull one of the spheres smoothly back over the disk so that it misses the other sphere. So here we have a picture showing this. So you have to be slightly careful. It's important to show that when you remove these two spheres, the remaining space is still simply connected, because the idea is then you can show, using some differential topology, that any loop bounds an immersed disk, and using some genericity or density arguments, any immersion can be replaced by an embedding. So this step is quite technical, so I'd refer you to the book, what was it, A World of... Yeah. Yes, that's the one, yeah, where it's explained in a bit more detail. But this is the idea, at least. Okay, so now let's return to the handle chain complex. So what happens when we cancel two handles? So effectively, so what happens here? So our k handle is cancelling with our k minus 1 handle. So in terms of generators, we should remove one of the generators for the group of k handles, one of the generators for the group of k minus 1 handles, and we can also think about the matrix. So the matrix of the boundary map from the group of k chains to the group of k minus 1 chains is an integer valued matrix, and if our k handle hki cancels with our k minus 1 handle hk minus 1j, it means that in the ith row and the jth column, or maybe the jth row and the ith column, you have a plus minus 1, so you simply get rid of that row and that column. Okay? And so in fact there's a reverse process to handle cancellation, which is handle creation, which is where you just add a cancelling pair of handles, and this does the opposite. This will add two generators and then add an extra row and an extra column in the matrix, which the row and the column will consist of zeros apart from one shared 1. Okay, so another technique is handle trading and handle sliding. So the idea is as follows. At some point we've attached a k handle. Let's try and attach a k plus 1 handle and a k plus 2 handle, such that the k plus 1 and k plus 2 handle cancel, but also the k and k plus 1 handle cancel, which means that we've traded a k handle for a k plus 2 handle. So the question is, when you can do this? Well, you can show, because of some dimensionality constraints, that you can only trade 0 handles for 2 handles and 1 handles for 3 handles. But I won't go through the proof. Another technique is sliding handles. So the idea is we can slide a K handle over another K handle. So we have a picture here where we're sliding a one handle over a one handle. So I guess this is the core. We're showing sliding the core over, and we can also do this. There's a picture where we're sliding a two handle over a two handle. So the idea is, what's the effect of this on the handle chain complex? Well, you can show that if you slide some K handle HK alpha over another K handle HK beta, then the boundary map changes as if we replace HK alpha by HK alpha plus or minus HK beta, depending on orientations. Or alternatively, what you could do is we could keep the basis fixed and then look at the matrix of the boundary map, and this corresponds to altering the matrix by elementary row and column operations.